Welcome to the deep dive. Today, we're kind of shifting our focus a bit.
Yeah, away from the usual suspects to the big proprietary AI companies everyone talks about.
Exactly. We're diving into what feels like the real engine room of innovation right now. Open weight large language models.
It's where so much disruption is happening. The past few years, it's all been these huge closed-off systems, right? Billion-dollar companies.
Hmm.
But the sources we're digging into today, they paint a really different picture. It's all about transparency, extreme efficiency, and this incredible push towards local specialization.
It feels like more than just the next step. It's democratizing things.
Totally. It's about making top-tier AI accessible. That's the core idea.
So our mission for this deep dive is pretty straightforward. Break down the key strategic moves and the tech breakthroughs that are making this happen.
We want to get you up to speed on how world-class AI development is basically opening up to almost anyone, regardless of budget or even the hardware they have access to.
We've got three main areas we're looking at.
All right. We'll kick things off with Llama. Can't really talk open weight without starting there. It's pretty much the standard bearer, and especially with their latest big releases.
Then we pivot to DeepSeek.
Yeah, the efficiency champion.
Mhm.
They're coming at this from a totally different angle cost. Their architecture is, frankly, shaking up the whole financial model of running AI.
And wrapping it all up, we look at InstructLab.
Which is just fascinating. It takes all this potential for model specialization and puts it, well, right on your own machine, your laptop even. It's about giving control back.
Right. So the goal is to equip you, the listener, with a really solid understanding. Not just what these models do, but why they matter, why they're changing the whole game.
Exactly. It's about the strategic shifts.
Okay, let's get into it. Llama first. What's the big deal with this whole open weight approach? So when we say Llama is open weight or open source, we need to be clear what that actually means in this context. It's not just free stuff.
No, definitely not just free. For Meta, releasing Llama like this is a massive strategic play. It fundamentally changes how people develop and deploy AI.
How so? What's the core difference?
Well, the key thing is access. The model, weights themselves, the core intelligence, if you like, plus the code used to train it, and even details on the data.
Mm-hmm.
It's all out there, accessible, usable.
And that accessibility leads to benefits you just don't get with closed systems.
Precisely. Three huge ones, really.
Yeah.
First up is transparency.
Right. If you're using a big proprietary model, it's basically a black box. Input goes in, output comes out.
And you have no real idea why it gave that output. You're flying blind, essentially, which is a huge risk if you're building a business on it.
So with Llama,
You can actually look inside. Developers can inspect the architecture, the layers, they can understand its strengths, maybe why it struggles with certain things, or where potential biases might creep in.
that sounds crucial for debugging or improving safety.
Absolutely. You can see why it might generate certain outputs, which is impossible when it's closed off.
Okay, transparency's one. What else?
Customization, adaptability.
Yeah.
Because you can see the engine, you can actually tune it.
Without needing permission from Meta.
Exactly. Developers grab the base Llama model and then fine-tune it. They use their own internal data, maybe confidential data, to make it specialized for their specific needs.
Or make smaller versions.
Yeah, that's a huge one. Distilling it down into smaller, really focused models for specific tasks. This is how you move away from those massive, expensive, do-everything generalist models.
Which leads to the third benefit,
Yeah.
accuracy and efficiency.
Right. It kind of circles back to the community aspect. Because you have potentially thousands of eyes on it, researchers, developers all over the world inspecting, tweaking, improving.
You get faster innovation.
You get faster development of smaller models that punch way above their weight in terms of accuracy compared to the giant closed ones.
And smaller means cheaper, faster.
Exactly. Better accuracy in a smaller package means less computing power needed, lower running costs, quicker development cycles. Llama's whole strategy, right from the start, was about nailing that specialization, performance within a size limit.
Their models were often way smaller than the proprietary giants, right?
Substantially smaller, yeah, but often competitive on specific tasks.
Let's trace that evolution quickly because it happened incredibly fast. Llama 1, February 2023.
Yep. Llama 1 basically created the market for these powerful but smaller models. Sizes from 7 billion parameters up to 65 billion.
Before that, everyone thought bigger was always better.
Pretty much. Llama 1 showed that smart design and good data could give you great results without needing, hundreds of billions of parameters.
Then just a few months later, July 2023, Llama 2 arrived.
Right. Similar size range, 7B to 70B, but the focus was really cranking up the performance within that size. Better bang for your buck, essentially. Maximize that size to performance ratio.
And then came the specialization focus.
Almost immediately. August 2023, they dropped Code Llama.
Which wasn't just a tweak, right? It was purpose-built.
Totally. Models designed specifically for generating and understanding code. They even had one just for Python. That was a massive gift to developers.
And this theme continued with Llama 3 in April 2024, still focusing on performance for size.
Yes, largely sticking to that 7B to 70B range and consistently pushing the performance envelope, often beating bigger proprietary models on benchmarks.
But then, July 2024, Llama 3.1, things changed.
Yeah, 3.1 was a major shift. It wasn't just about efficiency anymore. This was Llama stepping into the heavyweight ring.
Because of the 405 billion parameter model, that feels like a huge departure from the smaller is better strategy.
It was enormous and definitely a departure. But I think the statement was clear. Open weight isn't just for niche applications or efficiency plays. It can scale to compete head-to-head with the absolute biggest, most capable proprietary models out there.
And crucially, even at that massive scale.
Still fully open source, which cements Llama as the platform for the whole open community, from small scale to massive scale.
And 3.1 wasn't just about size, right? There were key technical innovations, too.
4 big ones, really. First, multilingualism got a serious upgrade.
Earlier llamas could do other languages, but English was definitely king.
Right. 3.1 was explicitly trained to be much more fluent and capable across a whole bunch of different languages. That's huge for global adoption.
Second, context window expansion.
Yeah, basically the model's working memory got bigger. It can handle much more information, more text, more data in one go.
Which is great for long documents or complex conversations.
Exactly. Analyzing big contracts, summarizing books, holding a really long, coherent dialogue, it boosts the model's capacity significantly.
But doesn't a bigger window create security risks, like prompt injection?
Yeah, that's the trade-off. A massive context window is a bigger attack surface. You could hide malicious instructions deep inside a long document you feed it.
So how did they handle that?
They introduced tools like LlamaGuard. Think of it as a security checkpoint for the input.
It scans the prompt before the main model sees it. Sort of. It looks for patterns known to be associated with harmful requests, jailbreaks, or these injection attacks. It's a necessary safety layer when you make the context window that large.
Okay, so multilingualism, bigger context window with LlamaGuard. What else?
Well, the fourth was really the power and scaling itself, releasing that 405B model, making that statement.
Oh, this huge model, it's not really intended for just chatting, is it? The sources mention more advanced uses.
Right. It's positioned more as foundational infrastructure for data scientists and engineers.
Like data generation. That sounds interesting. Getting good training data is always a bottleneck.
A massive one. It can take weeks, months sometimes, of labeling and cleaning data.
So the 405B model can create data.
Exactly. It uses its vast knowledge to generate high-quality synthetic training data on demand. What used to take weeks can now potentially be done in minutes.
That's a huge productivity boost for anyone building ML models.
Game-changing for the ML lifecycle.
It also acts as a teacher. Knowledge distillation. Yeah. You use the giant 405B model with all its performance to train smaller, more efficient student models.
So you're transferring the smarts.
Pretty much. You're passing on its reasoning ability, its knowledge structure, into a smaller model that's maybe specialized for a specific task. You get the benefits of scale without the running costs of scale.
Clever. And the LLM judge concept, using Llama to evaluate other models.
Right. Instead of relying on human opinions or simple scores, you use Llama 3.1 itself as a sophisticated judge to compare how different models perform on specific tasks.
So you get a consistent data-driven way to pick the best tool for the job.
Exactly. Objective evaluation across your different models, open or closed.
Okay, that brings us to the very latest Llama 3.2 from September 2024. If 3.1 was about scale, 3.2 seems to be about breadth, multimodality, and the edge.
That's a good way to put it. The vision expands way beyond just text. They're moving towards models that can handle complex tasks involving different types of information.
Like images.
Images, yes, but also potentially sensor data, weather info, connecting language to the real world.
And they delivered image capabilities straight away.
They did. New models, from 11B up to 90B parameters, focused on image reasoning. Not just seeing cat, but understanding context in an image.
What kind of context?
Think document understanding. You feed it a complex chart or diagram. Instead of just reading a caption, it interprets the visual data. You could ask, why did sales drop in Q3 based on this graph?
Wow, that's huge for business intelligence.
Or visual question answering. Show it a photo. Ask complex questions about what's happening in the scene. Is that person wearing safety gear? Which car is moving fastest? It's giving the LLM analytical sight.
Image captioning too, presumably.
Yeah, better, more context-aware captioning. Vital for accessibility and content management.
But the other really big news from 3.2, the one that maybe affects everyday users more directly, was the lightweight edge models.
Oh yeah, this is potentially massive. Tiny models, 1 billion, 3 billion parameters, designed specifically to run directly on your device.
On your phone, your laptop, without needing the cloud.
Exactly, on the edge. This means AI applications can run locally, super fast, without latency, and critically, without constantly sending your data back to a server.
Which is a huge win for privacy.
Massive. Your personal data chats, notes, location stays on your device. That's a major differentiator.
What could you do with that?
On-device summarization is a key one. Summarize long email threads, chat histories, your calendar for the day, instantly, privately. Generate text messages without lag. It opens up a lot of possibilities for personalized private AI.
And they introduced the Llama stack to help developers use all this.
Right. It's basically a set of tools and guidelines to make it easier to plug all these different Llama pieces, big models, small models, text, vision together into applications, especially for building AI agents. It simplifies the plumbing.
Okay, so Llama is providing this incredibly powerful, scalable, and now multimodal open platform. But that 405B model, even open, still needs serious hardware, which inevitably raises the question of cost.
And that is the perfect segue into DeepSeek.
Right. If Llama is about open power, DeepSeek seems laser-focused on making that power radically cheaper.
That's their angle, absolutely. This Chinese startup basically stormed in saying, we can match the performance of the big guys, maybe even beat them on some tasks, but run it for pennies on the dollar.
Their main target seems to be models like OpenAI's, right?
Yeah, the source mentions their O1 model equivalent. DeepSeek's whole pitch is same or better results, drastically lower operating costs.
And the cost claim is staggering. What was the number again?
DeepSeek R1, their reasoning model, is reportedly about 96% cheaper to operate than a comparable proprietary model.
96%. That's not optimization. That's a different paradigm.
It completely changes the economics. Suddenly, running sophisticated AI isn't just for giant corporations.
Yeah.
Startups, smaller companies, individual developers, the operational cost barrier just gets shattered.
How is that even possible? What's the secret sauce? It sounds too good to be true.
Well, it comes down to architecture. And the hardware numbers tell part of the story. Training their V3 model apparently took only 2,000 GPUs.
Only 2,000. Compared to Meta's Llama efforts using over 100,000?
Exactly. It's a completely different scale of resource requirement. Now, you have to ask, are they trading off something? Maybe breadth of knowledge.
That's what I was wondering. Is it as robust or stable?
It's a fair question. The sources suggest they achieve high performance, especially in reasoning, by being incredibly smart about how the model computes things. The key is efficiency and sparsity. It's not magic, it's clever design. Primarily, it's their use of the mixture of experts architecture.
MOE. Okay, let's break that down. How does MOE lead to a 96% cost reduction?
So instead of one gigantic dense neural network where all the connections are active for every calculation.
But it's a traditional model.
Right. With MOE, the model is split into many smaller, specialized subnetworks. These are the experts.
And each expert knows about a different topic.
Kind of. Each might be good at a different type of processing or reasoning pattern. Then there's a router, or gate.
What does the router do?
When a query comes in, say, asking it to write Python code, the router looks at the query and decides, okay, for this task, I only need to activate expert number 7 and expert number 23.
So the rest of the model stays inactive.
Exactly. Instead of firing up the entire massive network, you only use a tiny fraction of the parameters for any given task. Maybe just 5 or 10% of the total model size is active.
Ah, okay. So during inference, when it's actually running, it's using vastly less compute power.
Precisely. Which means lower training costs, too, because you're not updating everything all the time. But the big win for operations is that faster inference and much lower memory use. That's the engine behind the low cost.
And DeepSeek built up to this. It wasn't their first model.
No, they iterated. V1 was a standard transformer. V2 introduced MOE and some other tricks. V3, a huge 671 billion parameter model, refined it further with things like reinforcement learning and better GPU utilization. And that paved the way for the R series.
R1, the reasoning model. What's special about its reasoning?
The focus is chain of thought transparency.
Meaning?
Older models might just give you an answer. R1 is designed to show its work. It breaks down complex problems into smaller steps.
Like showing your math homework.
Kind of. It has this think time phase where it analyzes the problem. And the key thing for developers is DeepSeek makes this thinking process visible.
You can see how it got the answer.
Yes. How it broke it down, the steps it took, where it might have backtracked or corrected itself. You see the whole reasoning chain.
That's incredibly valuable for debugging or for industries needing explainable AI.
Absolutely. And this ability is linked to how they fine-tune it using reinforcement learning, or RL.
How does RL help with reasoning?
Well, standard supervised learning shows the model examples of how to get the answer. RL is more about trial and error.
You just reward it for getting the right answer, regardless of how. Sort of. With R1, the reward seems tied to the correctness and maybe the efficiency of the final answer. This pushes the model to figure out the best way to think for itself, to optimize its own internal reasoning process.
It learns how to reason better on its own.
That's the idea. This RL approach, combined with some supervised fine-tuning, is what gives R1 its strong, transparent reasoning skills.
This theme of efficiency carries over into their knowledge translation idea, too.
Yes, they use distillation. Take a big, smart teacher model like their R10, which uses MoE.
And transfer its knowledge to a smaller student model.
Exactly, making the knowledge cheaper and easier to deploy. But the really interesting part is model translation.
They can move knowledge between different types of models.
Precisely. They've shown they can take knowledge learned by a MoE model and transfer it effectively into a traditional, dense transformer model like a Llama architecture.
Why would you do that? Flexibility. Maybe you do your heavy-duty training on a super-efficient MoE system, but your company's existing infrastructure is better suited to running dense transformer models. You distill the knowledge across architectures.
So you train cheap, deploy flexible.
That's the power. DeepSeek basically decouples the high-end training efficiency from the deployment architecture.
Okay, so we have Llama's open power and scale, DeepSeek's radical cost efficiency. But how does an individual developer actually use this power to make something specific for their own needs? That feels like the final piece of the puzzle. Even with amazing models like Llama or efficient ones like DeepSeek, they're still generalists, right?
Exactly. And generalist models often miss the nuance. They don't have the specific jargon, the right tone, or the deep internal knowledge for highly specialized tasks within a particular company or field.
Like if you work in, I don't know, medical device regulation, a general model needs constant hand-holding.
Constantly feeding it context, rules, specific documents, which is slow and expensive. You're always prompting it with the same background info.
So the ideal solution is to bake that specific knowledge into the model itself.
That's specialization. You've fine-tuned the model so that domain knowledge is inherent.
And the payoff is?
Better answers, faster, with shorter prompts, because the model already knows the context. Lower costs, faster inference, built-in expertise.
But fine-tuning sounds hard. Doesn't that usually need big servers, data science teams, lots of GPUs?
Traditionally, yes, it was complex and expensive, and that's where InstructLab comes in. It's an open-source project designed to completely change that.
How? What does it do?
It makes sophisticated fine-tuning accessible, potentially even on your own hardware, like a decent laptop.
Fine-tuning a large language model on a laptop, seriously?
Seriously. It breaks the process down into 3 manageable steps.
Hey, what are they?
1, data curation, figuring out exactly what knowledge or skill you want to add. 2, synthetic data generation, automatically creating lots of training examples. And 3, efficient fine-tuning, actually integrating that data into the model.
Let's walk through it. Phase 1, data curation. How does that start?
You use their command line tool, iLab. It sets up your workspace. It also connects to something called a taxonomy repository.
Taxonomy, like a classification system.
Yeah, basically a structured way to organize the different types of knowledge or skills you might want to teach the AI, like company policies or product specifications.
And the first practical step is finding where the base model fails.
Right. You need to identify the knowledge gap. The source material you use is a great example. Ask a base model, say Merlinite 7B, which film got the most Oscar nominations in 2024?
And it probably gets it wrong, gives an old answer.
Exactly. Maybe it says The Irishman or something outdated. That failure point tells you what you need to teach it.
So then you provide the right answer.
Yes. You create a little file, usually YAML, with the correct question and answer. And crucially, you also provide a seed document,
What's the seed document?
It's the source of truth. Maybe a text file, a markdown file, containing the broader context, like the official press release about the 2024 Oscar nominations. This gives the system the raw material.
Okay, so you've identified the gap, provided the correct answer, and the source material. What's phase 2? Synthetic data generation.
This is where the scaling happens. You give it one good example, but models need lots of examples to learn properly.
So InstructLab makes more examples for you.
Yes, it uses a locally hosted teacher, LLM. This teacher model takes your single Q&A pair and the seed document you provided.
And spins up hundreds of thousands of variations.
Exactly. It generates different ways to ask about that information, different angles, related questions, all based on the seed document. Who directed Oppenheimer? How many awards did Poor Things win? It creates a diverse training data set automatically.
Okay, but wait. If an AI is just generating training data, how do you ensure that data is actually good? Couldn't it generate nonsense or inaccuracies?
That's a critical point. Garbage in, garbage out, right?
Yeah.
InstructLab includes a filtering step.
So after the teacher model generates the data,
The system runs quality checks. It filters the synthetic data, looking for coherence, factual consistency with your seed document, and avoiding too much repetition. Bad or irrelevant examples get thrown out before training.
that quality control sounds essential.
Absolutely vital to avoid messing up the model.
Okay, so you have your curated, filtered synthetic data. Now phase 3, training. On a laptop, how?
You kick off the training with a command like iLab model train. And the magic that makes it work on local hardware is a technique called parameter efficient fine-tuning, or PEFT.
PEFT, you mentioned that earlier.
Right. Often it uses a specific method called LoRa, which stands for low-rank adaptation.
Okay, Laura, how does that avoid needing a supercomputer?
So a base model like Merlinite 7B has, well, 7 billion parameters. Training all of them needs immense power.
Right.
LoRa cleverly avoids that. Instead of changing the entire massive model, it freezes the original weights and leaves them untouched.
So it doesn't modify the base model directly.
No. It inserts tiny new trainable layers alongside the original layers. Think of them like little adaptation modules.
And only these tiny new modules get trained.
Exactly. So instead of updating 7 billion parameters, you might only be training a few million at a tiny fraction of the computation.
And that's why it can run on a laptop. It might take a while, but it's feasible.
Precisely. It's computationally efficient enough for consumer-grade hardware, maybe taking a few hours.
And the result.
A new model version where that specific knowledge, the 2024 Oscar facts, is now baked in. You ask it the question again, and boom, gives the correct answer. Oppenheimer.
That's incredibly powerful for practical applications. Companies could train models on their own private data.
Without ever sending that sensitive data outside their own systems. Think about insurance.
Okay.
Train a model using InstructLab on decades of internal claims data, policy wordings, risk assessments. That model becomes an expert assistant for claims handlers, instantly understanding company-specific procedures and risks.
Speeding things up, reducing errors.
Massively. Or law firms. Train a model on all their past contracts, case law specific to their niche.
It could review new contracts much faster.
Spotting clauses, risks, inconsistencies based on the firm's entire history. Things a general model would completely miss.
So for the listener, this means they can take a powerful open source model like Llama
Use InstructLab to safely teach it their own specific private knowledge.
and end up with a specialized expert model they can run wherever they want, on-premise, cloud, even locally.
Exactly. It puts the power to create highly specialized AI tools directly in the hands of the user or the organization, breaking the dependency on external providers for that last mile of customization. Hashtag touchbag outro.
Wow. Okay, we've covered a huge amount of ground there. 3 really distinct but connected shifts happening in AI.
Yeah, first Llama really setting the stage with this powerful, increasingly capable open weight platform, pushing from efficiency right up to that massive 405B scale and now into multimodality and crucial edge capabilities.
Keeping things open, protecting privacy with on-device processing.
Then DeepSeek comes in with just brutal efficiency. That mixture of experts architecture, the focus on RL for reasoning, slashing costs by, what was it, 96%?
96%. Still blows my mind. Proving you don't need a nation-state's worth of GPUs to build top-tier models.
Right. And finally, InstructLab, the democratizer, taking that potential for specialization.
Especially using knowledge distilled from giants like Llama.
And using clever techniques like PEFT and LoRa to make fine-tuning genuinely practical on local hardware, on a laptop.
It really feels like the momentum is shifting, doesn't it? Away from monolithic, expensive, closed systems.
Definitely. It's moving towards AI that's more transparent, fundamentally cheaper to run, and crucially highly specialized for what you actually need to do. The one-size-fits-all approach feels like it's on the way out.
So here's a final thought to leave folks with. We've seen how you can take the absolute cutting-edge performance that Llama 405B teacher models knowledge and distill it down.
And then use tools like InstructLab to fuse that world-class general knowledge with your own specific private internal data.
Creating these incredibly potent, specialized models. So the question is, what happens next? What kinds of really specific, maybe previously unsolvable niche problems can you now tackle?
When the ability to customize and deploy AI of this caliber is literally right there on your own machine, and that massive cost barrier of hardware has just been, well, smashed.
What becomes possible then? Something to think about.
Definitely. Until the next deep dive.